Welcome back to the video tutorials on theory of computation, and we are discussing the unit which we call it as push down automata. So up till now we have seen all these concepts like representation and definition of a PDA. Then we have also seen how the PDA accepts and rejects a particular string. Then in the previous discussion we have had the types of acceptance by a PDA. We have also specified what is deterministic PDA and what is non-deterministic PDAs. Now the last topic which is left is equivalence of context-free grammars and PDAs. So just elaborate this with example. So we're trying to look for the equivalence of PDA and context-free grammars. Now why this is so is something like to define any particular language as a context-free language. I have two options, either to write a context-free grammar or I have to write or design a PDA moves, where grammars are said to be generative devices where it generates a particular string, and your PDAs are said to be an accepting devices. So it accepts a particular string or it rejects a particular string. So in this concept, firstly, we will see if a given context-free grammar, how it can be converted back to a PDA moves. Let's not worry about whether it is an empty stack or final state, because both are equivalent. If we could design a PDA with empty stack, I can revert back this to a final state. And if I can design a PDA with a final state, I can even go back and show the equivalence that the same PDA with the final state can be converted back to empty stack. So just now what we wanted to discuss is if the given context-free grammar, how it can be converted back to a PDA moves. So this is what we wanted to elaborate. So just begin. So PDA corresponding to a given context-free grammar. So given context-free grammar, how to convert it back to PDA. So there are at least two natural ways a PDA can simulate a derivation in a grammar. So something in a context-free grammar, any particular string, if we could derive, the same string can be accepted by a PDA. Naturally, can be accepted by two different ways. These approaches are either to design a top-down PDA approach or bottom-up PDA approach. We'll look back to this, what these concepts are or notions are. The first is we'll go for top-down approach PDA, to design a top-down PDA. So in the literature, the algorithm is given how to convert a given context-free grammar into a particular PDA moves. So in this, what is given is, so G is given. So G is consists of non-terminal, terminal. It is starting symbol of your context-free, your particular context-free grammar, and then the total number of productions that we have. So receiving these four elements, I need to design a particular M, which is corresponding PDA having 7 tuples. Now the algorithm says, while converting, how many state I should have in such a PDA. So it is clearly specifying I should have 3 states in the corresponding PDA, either it is Q0, Q1 or Q2, and this algorithm suggests I should have 3 states. Now the alphabets are finite set of alphabets, so whatever sigma your context-free grammar is working with, the alphabets remain same for PDAs. Now this is stack alphabets. So what can be available on stack? So it can be any non-terminal with corresponding to your grammar, any valid terminal symbol with corresponding to your context-free grammar, as well as the basic element Z0. So anything can be available on top of stack, where I consider Z0 is neither a non-terminal nor a terminal symbol. Now what is the first move that the PDA should design in the, it should take in the design procedure. So initial move of your M is to place S. What S is S is a starting alphabet of your context free grammar where the derivation starts with. So this S on the stack I need to push. So this mechanism is saying initial move of M is to place S on the stack and move back to Q1. So I was in Q0 state. This is the initial configuration of my machine is where delta is a single move representation. So I have being in Q0 without reading anything. When you have Z0 on top of stack, just move back from this Q0 state to Q1 and replace your top of stack, push the starting non-terminal of your context-free grammar onto the stack. This must be the first move that needs to be designed your PDA moves. This is it should be entered into your moves. The only other moves to the accepting state to Q2. Okay. Now when to accept, the condition is very clear. Being in Q1 state, the input should be exhausted and nothing should be left on top of stack. Now if this condition holds true, you need to go back to accepting state Q2 and Z0 remains. The stack will retain the Z0 as it is. We won't update the stacks. So in this, if you could see what is available on A consists of A Q2. So Q2 is accepting state within my PDA. Now, other than this is an accepting condition. So other than this, what are the other moves which expected to be entered into your PDAs? So step number 1, for every non-terminal A which exists within your context-free grammar, if this condition is true. So what that condition is, being into your Q1 state, if any non-terminal exposed on top of stack, okay, then without reading anything, the machine, the top of stack needs to be replaced by alpha. Now what this alpha is? So this is remain into the same state, but non-terminal should be replaced by alpha. If alpha producing alpha is a particular production in your G. If this condition holds true, you need to update your top of stack by alpha. And second is for every non-terminal which belongs to your grammar, and if this condition holds true, being in Q1, the input alphabet as well as the if terminal symbol appears in your top of stack, so it has to be eliminated by pop operation. Now this is the only mechanism the context free the algorithm suggests to work on. So we'll just go across a simple example and identify how it can be converted. So given context free grammar for foreign language, so we have already studied how to compose a grammar for a raised to n, b raised to n, where n tends to infinity, from 2 to infinity it goes to. So context free grammar for this is looks something like this. So what it should have, it has its own 4 tuples: non-terminal, terminal, starting alphabet, and your production rules. So S is a single non-terminal exists within your context free grammar. A, B, these are the terminal symbols. S is where the derivation starts with, and the production contains these 2 rules where the capital S is replaced, can be rewritten as small a, capital S and B. This capital S can be rewritten as AB to hold this condition true. Which condition? N tends to infinity, from 2 to infinity it goes. Now for defining rest of the conditions, so based on this 4 tuples, I need to define my 7 tuples. So compulsorily I should have a 3 states where Q0, Q1 is a non-accepting state and Q2 is an accepting state in this. So sigma is the same sigma which we worked on context free grammar. A and B retain the same. Now this stack alphabets can be any valid terminal, non-terminal, as well as Z0. Now Q0 is my initial state and Z0 is my initial stack symbol. Now my final state is, final means an accepting state is always Q2. Now deciding, following the algorithm, what the step number 1 says. So being in Q0, this is my initial configuration, Q0, without reading anything, when the Z0 is on top of stack, your starting alphabet of the grammar S should be pushed onto the stack, and simultaneously you should change your state from Q0 to Q1. Now this is the first move, has to be inserted in your PDA moves. Now what the algorithm says, so being in Q1, if any non-terminal appears on your top of stack, now in your grammar what is given, so S, it produced two rules, either S is producing ASB or S is producing AB. So these two rules, or these two rules of a context free grammar, has to be implemented in your step number 2. So what the intention is, being in Q1, whatever this non-terminal generates, so without changing a particular state, the top of the symbol non-terminal should be popped out of the stack, and whatever it generates into your context free grammar, it has to be pushed over the stack. So we'll push ASB on top of stack or AB on top of stack. Now the third element is, we look for all terminals which exist. So being in Q1, if the input is A and the stack alphabet is A, will remain into a Q1 state and nullify this. Same thing happens for B and will nullify the same. Now what is the condition for acceptance? There is a particular transition move which leads us from Q1 to Q2 based on the, if the input get exhausted being in Q1 and nothing is available on top of stack, so we'll move back from Q1 to Q2. So this is remains, so this is an accepting condition or accepting moves. Now as we have seen, there is two methods by which we accept a particular string in PDA, either by top down approach or bottom up approach. Just follow first the top down approach. So now we try to accept this X, A, B, which is A raised to 3 and B raised to 3. Now if this string, if it is can be derived from these two rules, so this is possibly, I won't elaborate all this. So step by step in the derivation, I could generate this triple A and triple B. So X is derivable from this starting alphabet of the grammar. So X is in the language. If X is in the language, then I have to, now using the top down approach of the PDA, the same string should be accepted by my PDA also. Now we'll go across, this is my initial configuration where we have a Q0, this is my string received, and Z0 is on top of stack. Nothing is available on top of stack right now. So being in Q0, the first move that the PDA will take is, it changes state from Q0 to Q1. Without reading anything, it push that S, which is starting alphabet of the grammar, on top of the stack. Okay. Now it realize if any non-terminal appears on top of stack. Okay. So we'll check back what this non-terminal can be replaced by. So I have two options. S, if it is on top of stack, either S can be replaced by ASB or S can be replaced by AB. Now, according to our requirement, so what the string starts with, A. Okay. And so keeping this in mind, so this S is replaced on top of stack by, with this production, ASB is replaced on top of stack. Now what makes it, see next in this case, so certain terminal symbol, once if it is exposed on top of stack, according to an input is available a terminal symbol A, so this is eliminated, the pop operation will be carried out. So only S is remains. So this A gets cancelled out against this A itself. Now what is left? Again, I need to find out a particular, start with S, A. So S with this rule is applicable, applying this rule. So this S is replaced by ASB, and A is again comes on top of the stack. So again we eliminate terminal symbol A against this input symbol, remaining into the same state, and again non-terminal comes on top of stack. So this last two symbol may be cancelled out against this AB. So what is left on input is AB. So to cancel out this, so this capital S, which is a non-terminal, is finally replaced by this AB following the particular PDA move. So we'll replace this by AB. Now if you could see, every element which is available on input one by one will get cancelled out. A is cancelled out by A, B is cancelled out, B is cancelled out, B is cancelled out, B. When the input get exhausted, being in Q1, if the input get exhausted and Z0 is on top of stack, now we will accept this by empty stack by popping this out of the stack. So this Q2 might be an accepting state, we'll accept, or we'll try to eliminate this Z0 from the top of stacks, but the string gets accepted. What this is a top-down approach. Why it is top-down? Because we start with the starting alphabet of the grammar and we try to eliminate this one by one, the terminal symbol match, and we'll come back to the null symbol. So we'll start with the top symbol and try to match the particular input with the particular moves of a PDA, and we could reach back to this accepting state. Now this is top-down approach. Now what if the same particular moves which we have designed, which if it has been asked with the help of bottom-up approach to following the bottom-up approach to identify the or accepting a particular string. So in this, certain string remains and we use two operations, shift operation and a reduce operation. Now what this shift operation and reduce operation is, we'll see one by one. So in context-free grammar, we have already pushed ASB on as a particular move of my PDA, and this AB is already been pushed while designing a PDA. So we'll refer the PDA moves for acceptance now. So what this table indicates, this is a move what we take, this is the production by which we apply this move, this is the stack contents which are available, and this is my unread-in. Now this is a bottom-up approach, means the string is available and from the string we'll try to reduce everything from a particular string to a starting alphabet S. Now first step is the input alphabet. If the stack is 0, it should be pushed onto the stack. So this is a shift operation we are doing, on which A is pushed onto the stack and remaining AA triple B is left it as it is on the input. Now we'll try to match whether any of the top symbols of the stack has the equal right hand side rule which has been applied. Now I have AZ0 and right hand side doesn't match. So I'll apply a shift operation one more time. So this A is pushed onto the stack. Okay, so stack contains A and the left character A triple B, left it as it is. Now again I'll check whether any particular context-free grammar rules match with this production rules ASB AB. So right hand side it doesn't match. So again we pushed a particular element. So this is a shift operation. We'll push this on to the top of stack. So this requires AAA on Z0 on particular stack and B is left on your particular input element. Now your stack works with last in first out order. Okay, so this B and A can be read in the reverse order if you want to try to match this with the right hand side production to reduce with. So this top AB is replaced by this S. So right hand side, if it matched on the top of the stack few elements, this elements will be popped out of the stack and across this will replace the left hand non-terminal. So this S will be pushed onto the stack by removing this BA. Okay, now this is called the reduce operation. So we'll reduce this two non-terminals by this S using this production rule. Now what is left? So SAA. So certain right hand side either would have AB or ASB. So nothing is matched. So we'll go for the pushing this B over this stack. So the stack contains B as A. If you read it reverse, it represent A as B, which is exactly the right hand side match, A as B. Now these three symbols are popped out of the stacks and we'll replace this three by the left hand non-terminal S. Now we'll again look whether it can be reduced further. Now if it is not, we'll just push this onto the stack and check whether this can be reduced with the reduce operation. So exactly if you read this ASB, it has got the ASB, and this right hand side can be reduced to non-terminal S. So will these three alphabets on top of stacks are popped and it is replaced by capital S. Now the last rule says if without reading anything, this non-terminal should be popped out of the stack and stack would be get empty. Now if the stack is empty or your top of the symbol S is available on top of stack, okay, see this is how we say that the string is accepted by bottom up approach. Okay, and I hope you understand the equivalence between your context free grammar as well as the PDA moves. And once a given context free grammar, if the context free grammar is given, how to convert it back to a PDA. Okay, thank you.